Good day to you all and welcome to this Motec webinar. My name's Dwayne Mitchell. The subject for today is what is a Motec power distribution module? Today we'll explain what a PDM is, what its advantages are, and the typical applications we'd find in the field. We'll also compare the wiring of some simple devices using conventional methods and also how we could do this with a PDM. We're going to discuss the functions found in racing and road applications, and we're going to take a look at the PDM Manager software, also have a look at how we can get extra output current, and finally we're going to cover the 4 different PDM model variants. Just a quick mention about Motec. This company was started in 1987 by Richard Bendel, and it's been in the forefront of motorsport for the last 23 years. Our products are basically focused on engine management and data acquisition, and we're based in Melbourne, Australia, where we do all our design and manufacturing. The building you're looking at is our Research and Development Centre, which is where we're currently located, and we have about 40 staff working in this building on development. We have 200 dealers worldwide, and we are in the forefront of both racing and road applications increasingly now. Okay, our team on the ground consists of 7 people in our department. I'm Dwayne Mitchell. I'm on the lower right-hand side of that screen. When you're dealing with us as support staff, you'll be speaking to one of us or emailing us, and we all have experience in virtually all of these products, while some of us do have specialities as well. Okay, so what is a PDM? A power distribution module. It's a device that's designed to replace normal fuses and relays and to simplify wiring, but also adding a great deal of extra functionality. We can use this device to switch outputs and, hang on a sec. Forgive me for one moment. I've just got a delay in my monitoring here, so hopefully things might be slightly less silly. Okay, so PDM is a device that allows us to control numerous outputs and at the same time customize how this happens, and gives us greater simplicity in the wiring looms, and also allows us to perform multiple functions from one device. Effectively, it's like a hub where all of the inputs and outputs are controlled from this device, and we can optimize how the driver interacts with the car and minimize the amount of driver attentions that's required to perform some functions. Okay, there are many advantages of using a power distribution module. Firstly, we can have multiple control strategies for individual devices. For example, we can use fuel pump control with multiple input parameters, for example, whether the fuel pressure is operating correctly and whether these supplementary fuel pumps are required, and all of these functions can be controlled without the driver's intervention. Secondly, the device itself operates like a digital fuse for each of the outputs, and that means that multiple conditions can be set, and this will allow fail-safe operation in a racing situation where a normal fuse would simply trip out and disable the car. Because this is a computerized device, it can monitor all of the voltages and currents for each of the outputs and inputs, and this information is used to make decisions at a very high speed and allow constant retrying, for example, of faulty outputs. And this adds to the protection and reliability of the device, where it effectively can allow a vehicle to operate in a limp mode, where again a normal race car might just simply be disabled and stop on the side of the road. Normal applications would include the same, all of the racing applications that our devices are normally used for. So the benefit of the PDM is that we can have a smaller, lighter application. We can simplify wiring, and this applies to virtually all forms of motorsport and is also extremely useful in road car applications. Now we're just going to take a quick look at how you might see a normal wiring application versus what a PDM is going to offer you. Now this is of course a very simple diagram. What we have on the left is how we would conventionally wire a few simple devices such as a fuel pump and a thermofan, and we would normally have an ECU that has individual output control for each of these devices, and then that goes via a relay and perhaps via a fuse for each of the individual devices. So firstly, what we're seeing is a fair bit of wiring and a fair bit of high current wiring, and then we have a bunch of individual relays and fuses. On the right hand side, we have the same functionality delivered by the PDM. In this case, we only require one very large power feed into the PDM from the battery, and then this sources all of the required outputs, including fuel pump, thermofan, and the ECU power itself. As you can see, there are no relays and there are no fuses because both of these functions are performed by the PDM device. So this allows us to, even in a simple application, we can reduce our wiring complexity, but it doesn't take much imagination to see that if you had a very large, complex wiring loom, this PDM is going to give you a massive reduction in wiring. So now we're just going to cover quickly a few things that you might typically see in a race application, and these are all functions that the PDM is again very capable of and offers a great deal of flexibility. Firstly, we can switch to the reserve fuel pump very easily. This might be something that normally the driver would have to be alerted to and throw a second switch on the dash if they lose fuel pressure or engine power. The PDM can monitor the fuel pressure, and it can also monitor the status of each of the pumps, and if the main pump starts to fail or is for some reason causing a short circuit, the PDM can then start using the reserve pump. In addition, it can notify the driver by using an alert on the dashboard, but it can also run these functions in the background. Another simple function is a turbo or engine cool down timer. This is typically used when you stop the car. We want the engine to run while the turbo cools down, and these functions can easily be run by a PDM. We can run timed outputs which control relays. When the ignition is turned off, then these timed outputs will retain power to the fans for as long as is required and eventually stop the engine as well. Another simple output function which is made a lot more flexible with a PDM is normal pump and fan control. Now typically engine cooling fans just have thermostats or other such temperature sets. If you have a PDM, you can set both the high and low temperature points for your fans, or perhaps if you use an electric coolant pump, the same thing could apply to that. And the benefit for this is that there are many race engines that have an optimum temperature. For example, with superbike engines that are very high efficiency engines, most of them run maybe 75 degrees, but there are some engines that would be better at 85. And so you can quite simply set the PDM to control either the electric water pump if you have one, or the fans, to keep the engine in the sweet spot, which means you'll operate at the best temperature with the minimum power loss. Another typical race function is to have flashing headlights when you're passing. This just is simply activated by pushing one switch, and the PDM takes over the control of the flashing speed, if you like, and therefore the driver doesn't have to think about that. They just hit the button and they get a multiple flash on their headlights. Same thing applies to rain lights. This can be done automatically by the PDM. Numerous inputs can be used for it to establish that there's a rain condition, and it can flash the tail lights in conjunction with stop lights if they're used. Another simple but very practical feature is an auto start function. The point of all of these functions is that they can be customized and programmed by you, and so that they're not obligatory, but that you can have all of this flexibility built in. The auto start function simply allows you to press the starter button, and the engine is cranked automatically until the ECU detects the run RPM, at which point the PDM will stop cranking the engine. A secondary benefit of this is a stall start function, which may be used in rally cars, for example, where a combination of pedals, if the driver stalls in a corner, they can just stomp the pedals and the engine will restart automatically. Now, these are things where the driver intervention can be quite simple, but the PDM can conduct a number of operations at the same time. Okay, so now we'll look at some functions we might find on road cars, because we also have a lot of practical applications for a PDM in road cars. The first one is a way of using an immobilizer function that might seem essentially that you can use to incorporate odd switching devices to operate as an immobilizer. For example, you use the horn button held down for a given amount of time to enable the ignition system. Another obvious application is operating indicators. The normal indicator stalk switches are just a straight switch, and the PDM has programmable flashing capabilities, and that means you don't need a flasher unit. So that's a simple function, but that can actually be combined. Demonstrate just a little bit later how we can use that in a dual function stoplight. Another thing that in some American cars in particular is quite frequently seen. So the PDM can also turn off headlights and courtesy lights and such things in the same way that a normal car might do that. And that means that we can use a PDM in a normal car and replicate all of the functionality of a typical road car, which is quite a useful feature. The other thing the PDM is very good at is in the situation where you have, for example, an alternator failure, the PDM can use a keep alive function whereby the important things such as the engine, the cooling system and so forth are powered, but the PDM can remove power from such things as the subwoofers or the air conditioning system, and therefore the car effectively has a limp home capability that would have otherwise been there. Now we'll just quickly have a look at the physical or electrical way these devices work. Effectively, we have a large number of inputs and outputs. Each of the PDMs uses a different number of inputs and outputs, and we'll cover that a little bit later. But what we're looking at is electronic switching, which means that the switch input to the device is the same as you would find in many ECUs, where there's a resistor of about 10k resistance, which goes to the 12 volt of the battery. And then what you have on the input pin is therefore a voltage which you can simply switch to ground in the same way that a set of ignition points would switch to ground. And that is the signal that the PDM uses to establish whether the switch is opened or shut. So that again is the way that most ECUs would input pins as well. Now, one of the benefits of this is that we actually only require a very small amount of current for this to be functional, in the vicinity of 1 or 2 milliamps. And that means that, again, we can use very small gauge wire for this sort of input wiring. The outputs are effectively a P-channel MOSFET, which you might normally know as a high-side driver. So these are the devices that perform as if they are a relay, but of course they have the added ability of monitoring current and then being used to control in a sophisticated fashion what is happening. So that is what the device does. It has a combination of inputs and outputs, and the benefit is that the device is actually normally fully powered all of the time, but it has a shutdown mode, a sleep mode, where it's really only pulling very few. It's about 5 milliamps in the sleep mode. So even in a normal road car, you can leave these things connected all the time. When you close the car off, shut the ignition and leave the car, 5 minutes later, the PDM will go into the sleep mode. But even under normal operating conditions, with the exception of the actual output current, the device itself only uses a very small amount of current. The other benefit is that the device has very low on resistance on the output drivers, typically 10 milliohms, which is 10/1000th of an ohm, and therefore there is extremely high current capability and very little heat generated in the device itself. So this is just a reliability factor, but it's also a way of getting a lot of control with very little heat. Okay, so again, if we look at the output device, what we're looking at is effectively a digital fuse. Now, the benefit of this is that unlike a normal fuse, which will trip out as soon as the current is exceeded, um, these devices, of course, will do that, but they have a great deal of tolerance which we can program into them, and therefore we can uh, effectively put delays or overcurrent thresholds, which means that uh, we can get a lot more sophisticated control of each output. So the fuse will shut down if the current goes over the current limit, but with certain conditions. But the principal benefit of this digital fuse is that we can set retries, or we can turn the power back onto this output after a certain delay, and unlike a normal fuse, which once it's blown has to be physically replaced. So the benefit of this is that, again, in a racing application, you may find there is a wiring fault or a fuel pump fault. The PDM will continue to try and keep these devices alive, even if it's only sufficient to get the car back to the pits. But again, we're not looking at a total DNF on the car. So the output of this fuse can therefore tolerate overcurrents for a short amount of time. And again, this is a programmable feature, and that means that we can allow our wiring system to work much closer to its rated levels, if you like, because we can set current limits very close to what the current might be expected to be. And if, for example, we have a temporary stall in a fuel pump where there's a large amount of current drawn for a very short time, again, a normal fuse would simply blow and you've lost your fuel pressure, but the PDM will firstly tolerate a very short current surge, and secondly, if it does turn off the fuel pump, it can be set to retry any number of times and within a very short interval. So that means that you can tolerate a certain amount of physical abuse, if you like, and the PDM is still going to recover the situation and keep the car running. Okay, so now we're going to take a fairly quick look at the PDM Manager software. I'm not going to explain how all of this is set individually, because that's a rather large topic and we will cover that in a later webinar. However, what we're going to do is just quickly go through a few of the screens and show you what sort of functionality we have. And principally what we're trying to demonstrate here is just how flexible this system is. So the idea of this software is that it allows us to design a unique setup for an individual application. And we call these setups configurations, and effectively you can custom design your setup for each whatever racing application you have. So each of the input devices, which can be the switches or CAN messages, and the output devices such as relays or pumps, can be named any way you like. This is a very flexible system, and it allows you to use normal English to describe each component. So what that allows us to do is to group components together, for example, switches or fans, and then they are stored in a hierarchical fashion. And in this example, we're looking at an engine as our main group, and then we have a bunch of fans, and in that group we have an output, a fan output, and a fan switch. So these channels are all just named in normal English, and they are in a hierarchical sense in the same way that the dots separate each of these subgroups, if you like. And then any of these names that we create as we're setting up our configuration are then flowing through to the rest of the device. And this is particularly useful when you're trying to set up things like input conditions, because you can name the devices as they actually are. And so it's very logical when you're trying to set up complicated logic conditions. Okay, so now the main benefit of this system is that firstly, we can see everything that's going on whilst the device is connected to a PC. And this is a very similar screen to what we call the view screen in our ECU products. So this one screen shows you all of the inputs, all of the outputs, and the individual and the actual status of the PDM as a whole. So what we're looking at here is just the input pins. You can see the body, horn, switch. Again, we're using this hierarchical naming convention. And then on the right hand side, we can see the pin that it's assigned to on the device. We can see its logical state, and we can also see the actual voltage on the pin. So clearly this is a very powerful way of seeing what's happening on the device at any time. Okay, so the other thing we of course want to look at is the outputs, and here we can see a fuel pump output, which is a typical use of this device. we can see whether it's the output pin that it's been assigned to, whether it's functional. We can also see the voltage, the current, and on the right-hand side we have a rolling graph which shows us the overall load condition of this output. Now, I'm not going to explain this in a great deal of detail, but it refers to what we talked about earlier with the capability to accommodate surge currents, for example, without tripping out. And so this is like a running average of how much load is on that particular channel. And again, you can see lower down, they're not highlighted, but we have other channels that are showing orange or red, and that means that they are closer to they're approaching the limits that have been set. Again, this is all extremely useful information and all available on one screen. Finally, we just have a quick look at the status, some of the status information. And again, we're looking at, this is for the actual PDM device itself. So we're seeing the overall battery voltage, the temperature of the unit, we're seeing how much total current is being switched by the device, and whether there are any error conditions. Now, the whole point of this is that all of this data is continuously available on the PC screen, and it's also continuously available as CAN data, and that's extremely useful because it can be transmitted and we can use this data in other applications. In other words, we can link the PDM to ECUs and dashboards via CAN. We won't go into a description of how CAN works. I'm sure you're all familiar with CAN. Let's just say it's a two-wire communications bus that runs at high speed. It's highly resistant to noise and interference, which is why it's used on vehicles, and it allows a vast amount of data to be shifted on a multi-drop bus. So the PDM is an active part of that bus. It can both receive and transmit on CAN, and therefore all of that information we've just seen is all available to other devices that might be on the CAN bus. So typically, in our case, we might be sending this to one of our ADL devices, and we can log all input and output channels, both for voltage, current, and for status, like for diagnostic values as well. So this information is, of course, extremely useful for analysis after the event, and we can see everything that's happening within the PDM. Secondly, we can use this same data to set off dash lights either immediately via outputs selected from the PDM, but they can also be transmitted to other devices such as an ADL dash, which has a similar set of trigger outputs. So in other words, we're sharing the data around. A switch that goes into the PDM can also be monitored and used by either an ECU or a dashboard as if it was wired directly into the ECU or the dashboard. Finally, the thing we can do with data, of course, is we can have alarms for the driver, what we call driver alerts, and therefore, again, we can the devices on the CAN bus can make these decisions, and only when it's a critical piece of information do we need to alert the driver. So this is all done with a great deal of simplicity by this device. Okay, now again, we're trying to get through this this software fairly quickly, so I'll only be brief. We're back in the main screen here, and what we're looking at is the global setup. So normally when you're about to write yourself a custom configuration for this device, the global setup is the first thing you'd quickly do, which is how you select which PDM version you're going to use. You can see that you can assign CAN input and output addresses so that we don't have multiple devices clashing on the CAN bus, and we can also set a couple of status things on output pins. So this is all sort of an overall setup condition for the PDM, and then we will go on to the individual components that this custom setup is going to entail. So the first thing we need to look at is input pins. Each of the PDMs has a different number of input pins, but they all function in the same fashion. Again, we're looking at a pin that has a resistor up to the plus supply rail, and therefore anytime you need to actuate that input, you switch it to ground using a normal single pole switch. So these could be, for example, clutch switches, brake switches, dashboard switches, fuel pressure sensors, all sorts of things can be used. And we have a lot of control over how these inputs can be used to trigger other conditions or to operate other outputs. For a start, we can decide whether the polarity is going to be high or low on the input, which is a straightforward operation. We can set voltage levels for the on and the off conditions, and we can also set time delays for the on and off conditions. And this is all done very quickly and easily. In many cases, we would just use default settings because if we're looking at a simple switch input, we don't need a lot of other complexity. But the possibility is there to have quite sophisticated triggering conditions. Now, of course, apart from wired inputs, one of the great advantages of the PDM is that because it can share data with the other devices on the CAN bus, again, for example, the ECU or a dashboard, we can use data or status information from these other devices as if they were a hardwired input into the PDM. Once again, what this allows us to do is to simplify our wiring significantly and use, for example, brake switches to do various functions in various devices. So we can connect to any of our normal ECU 100 series devices or to a dash, for example, and therefore something like a brake switch or a brake pressure sensor can be transmitted on the CAN bus into the PDM, and then a similar set of input conditions can be set. Now, one of the real benefits here is that we can have receive channels coming as switch or status information, if you like, which would be, for example, a brake switch, but we can also monitor actual real values, for example, fuel pressure or brake pressure. So we can have sensors that are connected to our ECU, which are then transmitting their real values on the CAN bus, and we can set separate thresholds, for example, for brake pressure lines within the PDM itself. So this gives us an incredible amount of flexibility. The other thing that we can do with CAN is, because we have the ability to combine conditions to make decisions, we can bring in CAN data, for example, engine RPM and ground speed, and we can combine this data in numerous ways before we make a decision about what's to be done. So again, having a CAN input capability is extremely powerful, and it's a big bonus with these devices. Okay, so the objective of having these multiple inputs and these multiple devices is that we can make sophisticated decisions on how we're going to control our output channels by combining a number of input conditions. For example, switches, pressures, engine speed, road speed. Any number of these things can be combined, and there are two ways we can do this. We can do this individually for inputs or outputs, but we can also have global conditions, which is another setup screen in the Manager software. And by having a global setup condition, you can therefore control multiple multiple outputs from the same condition. For example, you may have some warning condition that needs to both turn on a secondary pump and illuminate a dashboard light. And so you can put this in as a global condition, and then both of the outputs can refer to that condition. So our software allows a great deal of flexibility here. So the conditions are the decisions that define how we control the channel. Each of these decisions can be a very complex or a fairly simple operation, and operations are if you like, the individual components of how these decisions are made. So the benefit of having this condition structure is, again, that we can use the same condition to do multiple tasks. Now, these are calculated 50 times a second, which in the case of most control strategies is extremely quick. If you consider that we're looking at things like brake lights, fuel pumps, and so forth, that's a very high speed to give us a very good control. Now, I'll just quickly describe on the right-hand side. This is our a condition setup screen. And this is just a fairly straightforward function, but one that would normally be rather difficult. And what it is we have a number of, for example, American cars that don't have indicator lights. They simply have a stop light. And what we would like to do is have a function whereby the rear brake lights also operate as indicators. So what that means is we have an indicator switch and we have a brake switch. And if you look down, what we're seeing is the right brake light will come on if the brake switch is true, meaning that the brake switch is on, and also if right flashing is false. Now, that might sound a little bit odd, but what that means is we've already set up a condition called right flashing, which means when you turn on your indicator, it generates a pulse stream, which is the normal indicator blinking rate, and we've called that right flashing. So I'm using this condition to decide when my brake light is on. If the right flashing is not on, then the brake light just simply switches on. If the right flashing is also turned on, what my function now allows me to do is actually blink the brake light off. So if I have my brakes on and my indicators on, what I'm seeing is a constant brake light which blinks off momentarily. Now the second condition below that is when I'm not using the brake light, and it is effectively the inverse. So therefore, when my indicator is turned on but there is no brake light, I want my normal flashing rate to show on the same output. So you can see from this that this is quite a sophisticated way to get multiple functions into a single light. And in fact, we have a number of different versions, or let's say a number of options in the software where we can define this same condition using different operators. So it's a very complicated but at the same time flexible system. Okay, now we're not going to spend a lot of time on the operators, but this just gives you a demonstration of how many different possibilities there are. So if we just consider the example of two inputs, we may have two different switches and we have logical operators. So the first table you can see there is the equivalent of an AND table. What that means is we can have, for example, two switches, and only if both of those switches are on will the output be on, and that is the bottom condition where we have true, true, and true. Okay, so we can have multiple logical operators. We can use true, false, and, which is the one we're looking at, or exclusive OR, and that exclusive OR is another function that would allow us to do the same brake light with indicator function that I've described before. Okay, now the graph on the right-hand side is called a conditional operator, and what this allows us to do is monitor, for example, current or brake pressure, and we can set this output to only be active if the value matches perfectly a particular value. So in this case, we're looking at a value of 4. That will turn the output on or make it true if you like. Now if we go down to the middle one, this is a time function. And what we're looking at there, that is the left middle one, I should say. So what we're looking at here is functionally what we would use for a flasher system. It's actually called a flash function. So when I turn my input switch on, I can program the rate that the output switches on and off, both in terms of the on time and the off time. And so this is how we would drive a set of flashes. And again, all we're looking at is a simple switch on the input, but this output function is going to give us some flexibility. Okay, now on the right-hand side, we have what we call an edge-based triggering. I won't go into a great deal of detail here. Again, what we're looking at is just the fact that there's a vast number of possibilities for individual conditions, and all of these operators can be combined for more complicated functions. The last one is a little bit more complex. It's a hysteresis example. Hysteresis is simply a switching function that has both a high and a low point, similar perhaps to what you would do with an engine fan. So we have a high temperature there and a low temperature. Once we reach 70 degrees, for example, our output turns on, and then once we get below 40 degrees, the output turns off. So that's what hysteresis is. It's simply the ability to have two different switching points controlling the same output. So again, what we're looking at is a very sophisticated set of combinations, and they can all be used together in multiple modes, if you like, to get quite sophisticated control. Okay, so now we're going to look at how the outputs are set up. Of course, each of the devices you have connected is going to have different requirements, and so the individual outputs have to be configured for which device they have connected to them. Clearly, a blinking indicator bulb is going to have a different requirements to a high pressure fuel pump, for example. So each of the output pins is therefore defined, named in a simple term. For example, lights high beam. So again, we can use simple English or whatever our chosen language is, and we have a completely unambiguous name for what that function is going to perform. Below that, we can set how much current we're going to allow. We're going to set whether we're going to allow the digital fuse to retry if it trips out, and we're going to say how long it needs to wait for before it does that, and also how many retries we're going to allow. So again, we can set up quite elaborate profiles here, and that means the fuel pump is the perfect example because they are frequently things that fail, and this structure allows us to keep them alive for the absolute longest amount of time. Now, what you see at the bottom of this screen is another example of our condition setting. So as well as our global conditions, we can set individual conditions just for this particular output. And once again, it's composed of the same operators and input and output functions that are combined in a logical fashion. So this would be the case of a unique output where we only need to have this degree of logic for this particular output. Okay, now what happens when you generate these output channels is that they also provide data which is available again on the CAN bus or on our view screen for control, status, voltage, output current, the actual status of the device, and again the load profile. Now you may wonder what the difference is between current and load. The current is the instantaneous current going through the device, and the load is, as I described earlier, it's like a rolling average of the overall load on that output. And this is the way we allow, for example, surge currents and other short-term intermittent currents to not just trip the system out. So both of those parameters are interesting and useful, and again, they can both be logged. Now, the other thing we have is that these devices, the high current outputs are capable of 20 amps each, but there are some situations where we need more than 20 amps. And it's as simple as wiring all of these outputs together. So we can combine them in 20 amp chunks. The other outputs, there are two output types on these devices. We can't combine the 8 amp types with the 20 amp types, but we could combine a number of 8 amp types together to get, for example, 24 amps. And now this is a good example of where we use our global conditions to control an output. For each of these outputs, there would be no point in setting up an individual logic equation, if you like, because I can set it up as a global condition, and then each of these outputs just simply refer to that global condition. So it's a much faster way to set the thing up. Okay. So now we're just going to quickly look at the other benefits we can get out of these devices. As we've mentioned, we can reduce our wiring cost. As the normal wiring required for switches and so forth is usually wired in, say, 20 gauge or 18 gauge, we can reduce this down to as low as 22 or 24 gauge for switches. We can therefore have a much lighter wiring harness with fewer, less wiring, less distance of wiring, if you like. Of course, the outputs still require sufficient, wire for the amount of current they're expected to carry. We can also combine more than one PDM in one vehicle in the same way that we have, for example, a PDM and an engine ECU and a dashboard. We may have a PDM at the front of the car and another one at the rear of the car. Now, the benefit here is, again, that we can reduce our wiring massively because all of the data that both of these devices need is carried on the CAN bus, which is a simple pair of wires. So we can therefore have two power hubs or more in a car. Each of those power hubs then fans out to the individual devices at the front or rear of the car. But between those two devices, we only need a power feed from the battery and a CAN signal, and they can interchange both the input and output statuses, and a switch at the rear of the car can control a device on the PDM at the front of the car. So again, we've reduced our wiring significantly. The other benefit is we can actually reuse switches for different functions without having to rewire the whole vehicle. We simply redesignate what that switch function is, or we combine it in a different way in our logic setup. We can also use one switch to perform multiple functions. The simplest example of this is a switch, for example, a press button. We can time how long it takes this press button to be pushed, and we can have, if you like, you can stab the button for one kind of switch operation, or you can hold the button down for another kind of switch operation. So even in the case of an automatic start, you might have a short stab to prime the fuel pump and then a long stab to start the engine. So the same switch is actually being used to do two different things. Okay, now we're just going to have a look at the actual devices that we're currently producing. You can see there are 4 of them. We have a typo in our screen. I apologise for that. Those connectors are not called Autosport connectors, they're called Autosport connectors. So the 2 devices on the left are manufactured using billet machined aluminium cases, black anodized, and they use Autosport connectors, which are, of course, the very high quality connectors that we use for a lot of our products. These devices are virtually explosion proof and bulletproof, not quite. Okay, so we have effectively two case sizes. One is larger than the other. the PDM32 has 8 20 amp outputs and 24 8 amp outputs, and the 16 has the same number of high current outputs and fewer low current outputs. You can also see that the PDM32 has 23 switch inputs and the PDM16 has 12. So clearly they're designed for a greater or smaller sort of sophistication depending on the application. And we've also recently introduced the PDM30 and PDM15. They're the devices on the right-hand side. They're in a cast magnesium case with an extremely high temperature coating, and they use the lower cost plastic connector, which you may also find on our M800 ECUs. And this is also an extremely high quality connector with gold-plated pins, but it allows you to get into these devices at a lower cost. They have a similar number of inputs and outputs, and of course the software can be set for any of these devices. So one version of the program will allow you to control any of these devices. Okay, I apologise if I've gone too fast, but we've been trying to cover a fair bit of material. Clearly there's a great deal of extra information available, and we will probably do some further webinars on this topic. However, we do have, this will be recorded and you'll find it on our website, and in addition we have our Motec forum where the same staff you saw earlier in this presentation are available, as well as other users of these products. So that's a very good way to get further information, and we would suggest if you have any questions you might wish to go to the forum, and one of us will be able to answer them in fairly short time. Okay, thank you very much for attending. That is the end of this webinar. We're going to keep the page open just for a few minutes in case there are any questions. We have a few other of our operations staff here who are very experienced with these devices, so if you have any tricky questions, they may be able to help you. Thank you very much.